In section 1 of chapter 7, you are going to be given two major ideas or two major concepts. The first part and the very last part deals with radicals. Now, radicals is something that we covered before in chapter 1, section 4. And so I have a full set of notes on that. If you need it, feel free to go back to 1.4 notes. And the only other thing I have to say about radicals is that on numbers 25 through 30, we are going to skip those for now, and we are going to do those at the start of the 7.2 notes. So if you see those, you can kind of circle them just to remind yourself that you're not going to do those today. That the plan is we're going to do those on Wednesday, because I felt like there was too much to cover in 7.1 if I were to throw that extra stuff in there. Okay? So, to remind you, when you're simplifying radicals, insides, radicals, multiply other insides of radicals, you can reduce or simplify them by doing the factor tree, by circling any pairs. For every pair, we cross them out and move one factor outside the radical. That's what we did before in chapter 1, section 4. If you don't remember, go back there. I will show you at least two examples just to remind you how to do it. The other thing that we get to cover is the Pythagorean Theorem. The good thing about that is you covered that in 8th grade. A squared plus B squared equals C squared. It's where the two legs squared added together will equal the hypotenuse squared. And there's this neat little proof that I found on the internet. Let me see if I can pull it up for you. Here's a triangle. And in the triangle, that's A squared, that's B squared. And this other side is C squared. There's a square on each of the sides of the triangle. Just look at that. Isn't that so satisfying? Watch this again. Watch. That's C squared. They're going to rotate it and let the water drain from C squared into A squared and B squared. Perfect! It's beautiful. It almost makes me want to cry. How pretty that is. I don't know if you find that neat, but I do. I think that's... let's cover all this up. We don't need to see any of this stuff. Let's get rid of that. And go there, and where was I? There we go. That YouTube stuff, let me tell you, it's hard to control. Anyhow, C is always the longest side. A and B can be switched around when you're using A squared plus B squared equals C squared. We just got to make sure it's in the right spot. And the reason we're dealing with radicals is because most of our problems are going to have radicals in either the answer or in the side, or in as a part of the problem. So that's why we're dealing with radicals. The last thing that we're going to do with Pythagorean Theorem that you may or may not remember is that you can tell if something is a right triangle or not based off of the Pythagorean Theorem. Meaning, if A squared plus B squared is equal to C squared, then it has to be a right triangle. If they're not equal, then it's either obtuse or acute. We used to go into this. We're not going to go into it this year. Instead, you're going to be asked, is it a right triangle or is it not a right triangle? So that's as far as we're going to have to go. If you wanted to know, we could figure out if it was obtuse or acute as well. So let's do some examples. You have a worksheet in front of you. You have number 5 in front of you, I hope. It says 2 root 6 times root 3. In our notes, it says insides multiply insides, outsides multiply outsides. This is an outside number. It's outside the radical. Outside the number is an invisible 1. Inside. So outside numbers would look like this. Inside numbers would look like this. There's kind of an inside of the radical and outside. Outsides multiply outsides, insides multiply insides. Now, you could multiply these numbers and make it bigger. 6 times 3 is 18, yes. But because the next step is factor tree, then just leave it like this, put them next to each other, and then factor it down into its parts. 6 breaks down into 2 times 3. And that will save you a little bit of time so that you can now know that the 6 is 2 times 3 times that other 3 when you're looking for your pairs. Your next step is to look for any pairs of squares. Circle any pairs, cross them off, and one of them can break out. That's what we covered in 1.4. If there's anything left inside, then you leave it inside and it multiplies. If there's more than one of these, more than one can pop out. That doesn't have a pair, it stays inside. What do we do with these numbers? We always multiply them when they're outside, and if that's it, that's our answer, 6 root 2. We're going to do the same thing for number 9. Number 9 is my next example. It says 3 root 2 quantity squared, which means we have a 3 root 2 multiplied by another 3 root 2. There's 2 of those factors multiplying each other. Outsides are going to multiply outsides. That's the 3 and the 3. Insides are going to multiply by insides. And I'm just going to put them next to each other. I'm not going to make it bigger, because then I would just have to factor tree, and that would make me split them apart anyways. 2 times 2 is 4, but now I have a pair. Circle any pairs. If there's a pair, you can pop that thing out. One factor breaks out. If there's nothing left inside the radical, then the radical goes away. The 2 is now an outside number. The 2 multiplies the 9. 2 times 9 is 18. My answer is 18. And just so you know, your calculators are capable of doing these as well. Just make sure you use the parenthesis button when you do your 3 root 2 parentheses squared. Your calculator is capable of doing the radicals as well, so keep that in mind in case you want to double check yourself. I have chosen number 14, 18, and 21, and those will be our last examples that we do. The reason why I chose those ones is because these ones deal with the Pythagorean Theorem, and they have these square roots involved, just in case you didn't know. Number 14 says, using the Pythagorean Theorem, find the missing side of each right triangle. Leave your answer in simplest radical form. They give you the B, they give you the C. You got to find A. They even give you a picture in case you need to see it. What I would do is I would start off with A squared plus B squared equals C squared, and then I'd plug things in. We don't know what A is, so it's A squared. B is 3, so I plug B in, and I would make that 3 squared. C squared is root 15. You would put the root 15 inside, and then you would square it.
For Luke.
Okay. Pass that back. And now we're going to simplify it. 3 squared is 9. Root 15 squared is a root 15 times another root 15. Those are both inside. You could make it bigger, but why do that? Save yourself the step. Put them both inside. Look for the pair. Pop that sucker out. And you just get 15. You could double check that on the calculator if you want to, but it's shorter to do it in your head. Subtract the 9 from both sides. 15 minus 9 is 6. And then to get the A squared by itself, you have to get rid of that square. The opposite of squaring something is square rooting something. Technically, when you square root a variable squared, this is always equal to a positive and a negative value. The only issue is, since this is a triangle, we only care about the positive distance. So we only care about the positive part of this answer, which is root 6. yards, whatever that would mean right there. Root 6. Root 6 is technically about 2.4 yards. But they ask us to leave it in simplest radical form, which is what we're doing for this answer. That's how the majority of your problems are going to be.
Are they going to ask us to not put it in the simplest radical form, like on the test?
Almost everything is radical form. There may be a decimal. That's going to start coming into play in 7.3 for sure, but not necessarily 7.1. Number 18, find the missing side. They don't tell you which one is A and which one is B and which one is C in this one. But you're supposed to know the longest side is always the C. The hypotenuse is always across from the 90-degree angle symbol. It doesn't matter which one is A and which one is B. You can switch those up. But we have a right triangle, so I'm just going to plug these things in. I'm going to say that A is x, a squared plus b squared, 3 squared, is equal to root 14 squared. Plug some things in and solve. Now I know what that is, but just to show you, 14 and a 14, they're both inside a circle. One breaks out. It's going to be 14. Subtract 9, subtract 9. To get rid of the square, we do the opposite, which is square root, square root. And when we square root a variable square, there are two possibilities, a positive and a negative, but we only care about the positive value since we're talking about a positive distance. It is root 5 meters. Root 5 meters. So our answers are just going to be in these radicals that we're using. The last example is 21. And it really is asking you, is this triangle a right triangle? State if each triangle is a right triangle. Show your work. The only way you're going to know if this is right, do not just base it off of this picture. Do not just guess whether it is or it isn't.
Did we make an announcement real quick?
Not right now.
All right.
Come back in 5 minutes.
All right.
And so, do not go off of the picture. What you should be doing is you should be using the Pythagorean Theorem to see, does a squared plus b squared equal c squared? Is this the longest side squared? 2 root 53 squared. 4 squared. 14 squared. You're checking to see, is this a true statement? So let's see. 4 squared is 16. 14 squared, I'm going to use my calculator to figure out what that is. It's 196. I'm going to take my calculator, put 196 plus 16, and I get 212. Over here, 2 root 53 times another 2 root 53 would be outsides. Insides would make a pair of 53s. 53 times 4 is 212. Are those equal to each other? What does that mean? That means that this a right triangle? Yes, it is. It is a right triangle because a squared plus b squared is equal to c squared. If it wasn't, it could be obtuse, it could be acute. We were just going to say no, it is not if it wasn't. But that's where we're going to stop our notes.